Succeeding in ecology requires a shift in perspective. To solve complex exam problems, you must navigate three distinct skill sets: the math of populations, the hard limits of survival, and the threats that move through a biological network. We'll start by defining the three Dutch terms that underpin these concepts. First is populatie, or population. This refers to a group of the exact same species living together in one strictly defined area. The forces acting on that group are divided into two categories. Biotische factoren are living influences, like a predator hunting for a meal. Abiotische factoren are non-living influences, such as water availability or shifts in temperature. Finally, the voedselweb, or food web. This is the network of feeding relationships that connects our specific population to every other species in the ecosystem. High-level exam questions focus on the interplay between these three areas. You must predict how a change in an abiotic factor or a food web disruption mathematically alters the size of a specific population. Biologists use the vangst-terugvangst method to estimate population sizes when they cannot count every individual. The calculation relies on the formula n equals n1 times n2 divided by n3. Here is how you apply it. N1 represents your first catch. You trap a specific number of animals, mark every single one of them, and release them back into the habitat. After allowing the animals to mix, you perform a second catch. N2 is the total number of animals caught in this second round, regardless of whether they have a mark or not. The point of friction for many students is N3. This variable represents only the marked animals found within that second catch. It is the intersection of the two groups. Put this into practice. A biologist catches and marks 40 mice. That is N1. A week later, they catch 50 mice total. That is N2. Of those 50, exactly 10 have the original mark. That is N3. Pause the video and calculate the total population, N. The answer is 200. By multiplying N1 and N2, then dividing by the marked recaptures, you find the total estimate. Misidentifying N3 is the most common path to a failing calculation on test day. Moving from math to environment, every species survives within a specific Tolerantia curve, or tolerance curve. The peak of the curve is the optimum gebiet, where the population is most successful. The outer edges are the Tolerantia grenzens. Past these limits, survival is impossible. In any given environment, the resource in the shortest supply acts as the beperkende factor, or limiting factor. This factor determines when a population stops growing. This creates a ceiling known as the draagkracht, or carrying capacity. This is the maximum number of organisms the habitat can support over the long term. No population grows exponentially forever. The biological and physical limits of the environment dictate a hard mathematical ceiling. The final concept involves how persistent toxins, which do not break down in the environment, move through a food web. Usually, 90% of energy is lost at each step up a food chain. Persistent toxins behave in the opposite way. They concentrate. This is accumulation. A predator must consume a large volume of prey to survive, so toxin concentration per kilogram of body weight increases at every trophic level. By tracing the diagram from water to seal, you see the concentration spike from near 0 to 160. As a result of this biological math, the apex predator becomes the most vulnerable organism in a polluted ecosystem. To see how these concepts unite, consider a scenario where accumulation kills off an apex predator. Without a predator to keep them in check, the prey population begins a period of rapid exponential growth. However, this growth hits a wall when the mice consume all available food. The population crashes and stabilizes at a new, lower carrying capacity, defined by the lack of resources. In any ecosystem, changing a single variable rewrites the math for the entire system. Take a screenshot of this frame as a reference for your final study session. Trust the data and read the axes of your graphs carefully. If you understand the mechanics behind the numbers, the exam becomes a simple matter of application. Good luck.